So, in the last classes now we have talked about the entire family of RCNN, right? And then we talked about SSD. So, what SSD, what did we talk about? We talked about the structure. In the structure, it is a very basic structure. What they have done is, for every feature that has been extracted from the convolution layers, what they have done is converted those features to find bounding boxes. If you remember very well, this is a very easy kind of architecture, and they have used VGG16 here, and they as total give out 8732 different boxes, right? So for each feature map it is either 4 boxes or 6 boxes. So one thing that I want to clear this out, and I think I was not very clear enough earlier when I talked about faster RCNN or when I talked about SSD. When I was saying the default boxes or the default anchor boxes, all that the model had to give out anchor box, or each anchors in a sliding window. For each anchor you need 9 anchor boxes. So what that means is, basically, see, the sizes of these anchor boxes are decided, alright. So the decided sizes are decided. So let's suppose we have 512 pixel square as the size, all right. So that is the size, and the ratio is 1:1. Okay, so you have one square box, and the size is this, and the ratio is 1:1, all right. So you have the box, you have the anchor box, and you have the center here. So what I meant is, these sizes have already been decided, and you get the size, the anchor boxes based on these sides. Now what you have to do is, in the regressor part, you need to find out these values: delta x, delta y, delta width, and delta height. So that means your initial values have already been decided. They have been given by the author itself, the one who has wrote about the entire paper, the researchers who have come up with this paper, alright. So you have the sizes and everything. So if your object fits perfectly and this is the center of your box, in that case none of this changes. But if it does not, then it has to be changed, alright. So that is when we say that, when I said the anchor boxes are, it gives out, each anchor gives out anchor boxes, what I meant is the anchor box sizes are decided. So for every anchor you are going to get anchor boxes of the same particular 9 sizes, alright. That has been given out. Now once you have these, what you can do is make the appropriate changes required, because it is easier to find the difference, alright. It is easier to say how much it has to be shifted rather than finding the actual coordinates by which it has to shift, alright. So that is what I meant with this whole thing, that it gives out the default boxes or the anchor boxes. Even in SSD, alright, even in SSD, the anchor box sizes and shapes have already been decided. Your whole thing out of this is, basically, when you are given such values, you have to find out how much it has to shift. That is done using a regressor. So that was the whole thing about faster RCNN and SSD. When I go back to the video and I listened to it, I realized this might have been a bit confusing. So I came back and I wanted to clear this out, alright. So now that we have this, what we will be talking about today is YOLO. YOLO means you only, I know you're going to say live, but it is you only look once. So this is the YOLO paper, and YOLO right now we have version 5, but we have had version 1, version 2. So we are going to talk about the most basic version, and then we will go and understand how it has changed over the years and what differences have come with YOLO 2 and 3 and everything, alright. So let us come here. So this is a very good presentation I found online, alright. So this is about YOLO, obviously, and this presentation is good because it helps in understanding about YOLO, but at the same time it is very good representation of the whole thing, right? So let's look here, then you'll understand. So this is basically a graph that shows the time. So now what has happened is, it shows when all of these models were released, alright. So MAP, this is basically, let me go back. So this is basically MAP versus the time in which the models were released. So one thing you can see, even if we have faster RCNN, right, you can see the number of FPS that it is using. So number of FPS is 7. So okay, So the FPS is 7. That means that even though it has a very good MAP, it is still slower. So it gives only 7 frames per second, which is very slow. I mean, you would notice everything. So hence we needed a better architecture. Then we had SSD, obviously. SSD was great and everything, but we also have YOLO, alright. So this here shows the version for YOLO V1. Over the years, this has improved and it has actually gotten very close to SSD and everything. So yeah, we use YOLO. YOLO is kind of better than SSD, I would say, and SSD is not used a lot actually. Okay, now let us understand about YOLO. So this starts with basically your input image. Alright, this is your input image. They have taken an example here. So your input image size has to be 448 cross 448 cross 3. Alright. So here if you will see, this is the basic structure of YOLO. It is a very simple architecture. There is not a lot here. So you have GoogleNet here, 20 layers of GoogleNet is being used. Then this is followed by 14 cross 14 cross 1024. These are the outputs that you get from the 20 layers of GoogleNet. Once you have that, you have added different convolution layers itself. Okay, so there is one convolution layer for 14 cross 1024. Then it is same thing. So the convolution basically is here, and then you have 7 cross 7 convolution here. So the thing is, this part is pre-trained. So we are using GoogleNet here. This part here, GoogleNet is basically InceptionNet version 1. This part here, this will be trained from scratch. So this is pre-trained, this will be trained from scratch. Here what you get is these outputs, 7 cross 1024 after doing convolutions, alright. And then you convert it into fully connected layers. You get 1470 cross 1 and you reshape it into 7 cross 130. Now why this 7 cross 130? We'll talk about this, alright. They have actually shown it in very proper way, but we will talk about this more. So you have 7 cross 130, and this 7 cross 130 helps in detecting the outputs here, the bounding boxes. Alright, so this is a car here, this is a bicycle, and this is a dog. So it has detected this. So how is this happening? We'll understand. So here what they have done is they show that they have used additional convolution layers to increase the performance. That they have done using basic experimentation and found out, okay, using extra convolution layers help in giving us a better performance. So now let us talk about this 7 cross 130. So when we talk about this, so what this represents is, now you have the image and your image is divided into 7 cross 7 grids. Alright. So if we were talking about different things, right, when we were talking about feature maps and everything, we talked about 8 cross 8 feature maps. They were used in SSD, right? We talked about this and we said how they were used to detect smaller objects like a cat in the image. And at the same time we talked about 4 cross feature maps, and this was used to detect a dog. If you remember in the last image when we talked about SSD, right? So in the same thing here, what we will do is we will divide the image into 7 cross 7 grids. Instead of using 4 cross 4 or 8 cross 8, here we will be dividing it into 7 cross 7 grids, and into 30 we'll talk about this. But yeah, so you have 7 cross 7 grids. So each grid box or each feature map box here, whatever you say, each grid box is responsible to give 2 bounding boxes. So if you remember when we talked about faster RCNN, right? Faster RCNN, this gave out what, 256 boxes around. Then we had 9 anchor boxes, right? Each box was responsible for 9 anchor boxes. We had SSD, then SSD was responsible for either 4 or 6 anchor boxes per grid or per feature map. Here we have YOLO, and YOLO is responsible to give out 2 boundary boxes. So now let us get back and understand the shape. Let us look here first. So you have the grid and each cell here is responsible for 1 grid. So here we have taken a random grid and we have showed this in the figure. Okay, so this is the thing. Now let us look into what 7 cross 30 actually represents. Here 7 cross 7 is there, but since we are using only 1 grid, so that is 1 cross 1. So 1 cross 30, what does this represent actually? So the first 5 features are basically the features of the yellow bounding box. Since each box or grid box is responsible for 2 anchor boxes, so we will have 2 of these things. But yeah, let us talk about the first anchor box. For first anchor box, we have 5 outputs. What are these 5 outputs? We have delta x for the center, delta y for the center. Now these are the same as faster RCN and SSD, alright, so there is no change here. Delta width and delta height. These 4 things are constant. So in the first 5 outputs, the first 4 are these, and the fifth output, so this is 1, 2, 3, 4. The fifth output basically gives probability of object. So if you have the bounding box, right, you get the coordinates of the bounding box, so the probability that those bounding box figures have an object, it gives you that value. Alright, so let us look here. So the first 5 values are basically coordinate of the center box inside the cell, then you have the y coordinate for the box center, so the center value here. These are the first 2 x and y coordinates. W and h are basically bounding box width and height, and C is basically bounding box confidence. So the confidence, that the probability that the object is in that particular bounding box. Alright, so these are the 5 values. The next 5 values, so these first 5 values represent this yellow bounding box. Alright, the next 5 values will represent this here, this bounding box. So 2 different bounding boxes. Alright, this one here you can see different scales. So this is more of a taller kind of box, and this is more of a wider kind of box. But this center, these bounding box are for this center grid cell. Alright, so the next 5 are again the same thing. You have the x coordinate for the center, y coordinate for the center, width of the bounding box, height of the bounding box, and confidence that that bounding box has an object. Alright, you got these 2 values. Now what are the rest? So that means we have covered 10 values. So 10 values are done, but we have 1 cross 30. So we still have 20 values left. So what are these 20 values? Let us look into that. So here it shows, okay, so these are 2 bounding boxes for each grid, and 5 value is for 1 bounding box. Alright, so this and this 2 yellow grids we have found. So one is a taller kind of box, other is a wider box. The next is, what are the remaining 20 values? So this 20 represents the number of classes. So the data set on which it was trained, if you remember, even the last time we talked about SSD, and SSD was trained on a data set that had 20 classes. Here also the remaining 20 represents the number of classes. So you have 5 bounding box 1 values, 5 bounding box 2 values, and 20 class cores. So class cores are basically that the object belongs to that particular class. Alright, so 20 number of classes. Now here let me show you. So one class core is basically probability. So let's suppose you have, this is the one that you are finding, right? So let's suppose we have the anchor box in this format, and this is the dog. So this will give out basically, so for the first 20 classes, right, so they will be supposed like this. Okay, so you have 1, 2, this is the first value, second value, third value. Let's suppose my first class is the dog. So this will give out the probability that my object is dog if you have an object given that object. So what this means is probability that if there is an object, then that object is dog. So that probability is given out in the first value. The next, suppose your next class is cat. So that will give out the probability if that there is an object, the object is a cat. In that way it has 20 such classes. Alright. So these are the values that you are getting. That means these are the probability values. These are conditional probabilities. If you might have remembered, these are known as conditional probabilities, and they mean what basically is the probability if that there is an object, the object is a dog. Let's get back here. So what you will be doing is, now basically you will be finding out class scores. So how do you calculate the class scores? Your class scores is basically your confidence score multiplied by your score that you were getting from these probability of the class value. All right, so this that you were getting the 20 values. So now you will be calculating class scores. So class scores are basically probability object. So probability that there is an object in anchor box 1 multiplied by probability of class 1 given object. So class 1, let's suppose, is dog. So this comes out probability that there is an object in anchor box 1 multiplied by probability that there is a dog if there is an object in the boundary box 1. Alright, so that is basically what this means. So what you will be doing is, now this class confidence score, this will be multiplied to all these 20 values. These 20 values are basically the probabilities that the object belongs to that particular class. So you multiply that, you get one value. But you have to remember, you are not finding it for one anchor box, you are having two anchor boxes. Alright, so you calculate this now for the second anchor box. So now you get scores. Now these are basically class scores for boundary box 1 and boundary box 2. Alright, so once more let us go back again. So you have this whole convolution layer. Now this is basic thing, there is not a lot to understand. What you get is 7 cross 7 cross 30 feature map size. Now this feature maps basically represents, if you have the image, you have to divide it into 7 cross 7 grid. And for each grid you will be bound to produce, or you will be bound to get two anchor boxes or two bounding boxes for each bounding box. So the 30 here stands for basically 5 values for the bounding box, 5 values for the another bounding box, and the remaining 20 values, these 20 values represent your class scores. So that is the probability that if there is a dog, so what if there is an object, then if that object is the particular class. So that is what basically the 20 here is. And now for the 5 basically represents what? So your 5 is basically your change in x coordinate, change in y coordinate, change in width, and change in height for your anchor box. Now what you will do, now you will find the class scores. Your class scores is basically multiplication of the value that you were getting here, that is the boundary box 1 confidence. That means this boundary box contains an object. You need to understand the difference between this score and this score. So when we are talking about these two, it is very important because one might get confused. So when you are talking about the first 5, okay, so for anchor box 1, so let's suppose there are 20 objects, object 1, object 2, object 3, and till object 20. Alright, so for the first anchor box, what you have, you first calculate that probability that that anchor box contains an object. So this is important. So that means any object, irrespective of the object, you have to check whether it has an object or it does not have an object. So this is basically, if you remember, like faster RCN, and this is basically calculation of, okay, is there a background or is there no background? So that is what this is being calculated. Next, what you are going to calculate, probability that it belongs to any of these classes if there is an object. Once you have these, you will multiply this. So what you are getting is basically a 1 cross 20 tensor value. Alright, but this is for first anchor box. At the same time, for the same grid, you have to also find out anchor box 2, values for anchor box 2. So now what you will do, this probability will be multiplied again. For anchor box 2 also you will get this probability will, and for anchor box 2 also you will be getting these score values. Alright, the confidence that it has that particular class if there is an object. You will multiply this whole thing, and again you will be getting a 1 cross 20. Alright, so for each grid you are getting how many values? For each grid you are getting 2 such 1 cross 20 vectors. See, for each one you are getting 2. So how many grids are there in total? So there is 7 cross 7 grids, that means there are 49 grids. So for each grid, if you are getting 2 values, so that means you are getting total of 49 into 2, that is 98 values. Alright, so now you understand what is happening. So basic thing that we have done, there is not a lot. This basic representation we have shown here what is happening. Okay, so now you get all these scores, class codes. All right, the next thing that we will be doing is, see here it shows you have 98 such bounding boxes, 7 cross 7 for each number of grids, and into 2 because each grid is responsible to find 2 such bounding boxes. So now you understand this part. You have the detection procedure. No, so now you have this whole thing. Okay, you have this feature map, this size and everything. This is passed through a detection procedure and you get these bounding box values. So what are these values? How will this pass through? Let us understand that. So you have these class codes right now. Okay, so you have bounding box 1, 2, 3, 4 till 98. So you have these values. So the next thing that you will be doing is you will be understanding how to calculate the scores. So that means if you have 20, 98 such values and 20 such classes, so you remember if it is like this, so that means this is the class code for object 1, class code for object 2, object 3, object 4, and this goes on till object 20. In the same way, class code for object 1, object 2, object 3, and this goes on till object 20. Alright, so you have this whole thing. So the first thing you will be doing is comparing all these values. So you have the bounding box values. Now you will be comparing. Okay, so this is my object 1 in the detection. So my object 1, let's suppose, is dog. So I will be comparing my dog value from here to everything that is the remaining. So you will compare it 98. So all these values, all these 98 values will be compared. So that is the first thing. So the first one basically represents your dog scores. Alright, next what we will do is, see now what you will do is, if you remember, we also talked about IOU. So you have such values, right? You have all the values. Now what you will do is, this is basically what is like calculating the IOU score. So you have a threshold. If your value is less than the threshold, you set the value to 0. That means the object is not there in that particular anchor box. That is what it means, because your threshold value is already low, and if the value is even lower than that, that means you do not have the object. What this particular value means is the probability that this particular class belongs in this particular anchor box. Alright, so if your threshold is less, if it is very less, the value is very less, that means the probability that it belongs to dog is very less for this anchor box. Hence you will set this to 0. Let us go back. Let me show this. See here, you have this anchor box. Let's suppose you have, this anchor box, this green anchor box. So my first class, let's suppose for this anchor box, the probability that it contains a car is going to be very less. So this, in that case, the probability that it contains a car, that will be set to 0. So that is what we are doing, alright. But the probability that it contains a dog is going to be high. So if that is high, we cannot set that to 0, alright. That is what this whole thing means. So once I have set the threshold to 0, so now some values are 0, some are not. So what I will do next is, I will sort this out in descending order. So what that means is, now this is just for the first class, by the way. I am not doing it for other classes. Only for the first class I am showing. So for dog class, now I have values. Some are 0, some are not 0. 0 means the probability that it contains the object is not there. So the probability is very less. That means the object, there is likely a chance that the object is not there. Hence I have set that to 0. Now what I will do is, basically I will arrange these bounding box values. So let's suppose the first value is 28. So bounding box 28 says, okay, so the chance that I have a dog in my bounding box is very high. So this becomes my first thing. Next, let's say it says bounding box 25. So the 25 bounding box says, okay, the chance that a dog is there in my anchor box is high, but not as high as 28. So you will have that also. So here you can see you have all these values. Now you have sorted it out in descending order. So the bounding box 3 has the highest value, that it contains a dog. Then you have bounding box 1, then 98, and ultimately at the end all the zeros are there, because after sorting it out in descending order, at the end you will have all the zeros, right? Now this is for one class. You will do the same for the next class and the next class and so on, alright? So now what you will do is, you will do a non-max suppression algorithm. So non-max suppression algorithm basically is used to remove the redundant boxes. So redundant boxes, to remove this, you will be doing non-max suppression. If you remember what I talked about in non-max suppression is, suppose you have their object here, alright. and you have this box here, at the same time you have another box here, at the same time you have another box here. So there are a lot of boxes. All these boxes have an IOU, a very high IOU, alright. So the threshold is higher, so you cannot give it a false positive. So you have 3 different boxes, they all represent one particular object. So in that case, these boxes are the redundant boxes and you need to remove them. Now that is done using non-max suppression. Now we will be talking about non-max suppression algorithm. So finally we have the non-max suppression. So we will talk about how it works. So non-max suppression algorithm is basically, so first of all what we have done is, see, we have not done anything right now, we are just writing the value of classes and where the object belongs. So in the highest value, if you remember, you had the class codes, you set those to 0 which do not qualify the threshold value. Once you have set that to 0, the next thing that you will be doing is basically sorting this out in descending order. So that is what we have done. Now we will understand how to solve the non-max suppression algorithm. So here you can see boundary box 47 is 50% sure that it contains a dog, boundary box 20 is 30% sure that it contains a dog, and so on. And final, these bounding boxes are, the probability that it contains a dog is 0. So that is why they are at the end. Now what you do is, the very first thing, this is bounding box 47, it shows, okay, so this is the bounding box 47 here and it has a 50% chance. So this is what it represents, okay. And this is bounding box 20. And this is the box that is been given out, these are the values. So now it says it has a 30% chance that there is a dog. There is a dog, and even this bounding box has a dog, but if we had to choose anyone, obviously we are going to choose this one. So this here, it says 20% chance because you see there are the paws here, a bit of tail here, so it has the dog, it's not like it does not have the dog, but we are not going to choose this bounding box again. So these boxes are basically redundant boxes. Then 0.1 chance here that you have a dog, alright. So these are different things that have come out. Now what we will do is, we will try to remove these things because the whole dog is just one dog. So we do not need so many boxes, bounding boxes. We need only one. Okay. So here, this is basically bounding box 98, your final bounding box here. And the chance that it contains a dog is 0. So that is what this is showing. So to start with non-max suppression, what you do is choose the bounding box with the maximum score. That is not going to be difficult because we have just arranged it in descending order. So our first value will always have the maximum value. Once you have that, what you will do is, you will compare it to other values. So now you will compare it to the next value. Okay, so suppose this is our value, maximum value. So let us label this as bounding box maximum. Once you have labeled that at bounding box maximum, the next box will be your bounding box current. Okay, now what you will do is basically calculate the IOU of these two. So you will calculate how much of these two overlap, because chances are, if they overlap a lot, chances are they both represent the same object. So that is what we are going to do here. We are going to find out whether both represent the same object or not. So now what we will do is calculate the IOU. So we set the IOU threshold as 0.5. So if both of these overlap for more than 0.5%, so in that case you will set the current value to 0. Because see, this is the maximum one, bounding box maximum, this has the highest score. So chances are it contains a dog and it has a very clear picture of a dog higher than this bounding box current. So in that case, but both of these overlap a lot. That means the chances are this green one is a redundant box and we need to remove that. So if the threshold value is greater than 0.5, then you set the score to 0. In the next, so see, here you have set the value to 0. The next, now what will happen is, now this has been solved, you go to the next bounding box. Now this becomes your bounding box current. Now this bounding box current will now be compared to the bounding box maximum. Now once you are now comparing this, now what will happen? Again you will do the IOU. If your IOU is greater than 0.5, in that case you set the value to 0. Here in this case we are continuing because the IOU is very less. So it is possible that here you have a dog. You are not sure, because if the overlap is lot, that means they both belong to the same object. But here, since the overlap is less, it might be possible that you have another dog here. Hence we will not remove this. Now in the same way it will go on for all the other boxes. So you will keep comparing. Here also you are comparing. IOU is greater than 0.5? No, it is not. So you continue. You do not change this value to 0. So now the whole thing has been done. The next thing that you will do is, now you will change your bounding box maximum. So this was your bounding box maximum. Now we will go to the next highest value. So now this becomes your bounding box maximum, 0.2. Now you will compare this to all the other values except the bounding box maximum that was there for the first iteration, which was this bounding box 47. Now you compare this again, and in the same way what you will do, check the IOU. If it is greater than 0.5, you set it to 0. Here these two boxes, the blue and the pink one, they are a very good overlap, so hence the bounding box is going to be greater than 0.5, so you set this to 0. Alright, so in this way what you will do is, you will compare all of these. Once that has been done, you will be left with a few pairs of bounding boxes. Alright, in this case we only have 2 bounding boxes left. So now in the same way what we will do is, we will do non-max suppression for the next class and the next class and so on. So this was how we did it for the dog. So just a quick recap, what happens is, you select the IOU. Okay, let me write this. So you select bounding box with maximum score, and then you compare it to all other bounding boxes. If IOU is greater than 0.5, in that case your other box confidence or score becomes 0. Then you change your bounding box max, and you go and do this again and again, and finally you are left with very little of the values that actually have some numbers in it. The rest are all 0. Now what will happen is, once you have done that, you will do that for the next class and so on, and for all the rest remaining 20 classes. Alright, so once that has been done, you are left with a lot of zeros, obviously, because half of the time it has become 0 when you were here finding out the threshold value. So some of those became 0 there. Then you are doing non-max suppression, and in non-max suppression most of them become 0. So finally you have understood about non-max suppression. So now you will draw the bounding boxes according to these values. We'll say how. So you will go for each bounding box, alright, and you will check, okay, now in this bounding box, is there a maximum index value, okay, and is there a score? If that score is greater than 0, yes, and you have the index there, yes, in that case you will draw the box, otherwise you won't draw the box. So here it will be checking, okay, so scores for bounding box 3 and the index for that score. So the index, that means if it is your 8th index, that means it is for the 8th object. So your class becomes the 8th object, and your score is basically the maximum of this value. So once you get that, those values, you basically decide whether to draw the box or you do not want to draw the box. Alright, so this goes on, and in that way you draw bounding box 3, you do not draw bounding box 1, you do not draw bounding box 8, you draw bounding box 4, you draw bounding box 97, and so on. Alright, in that way you have this whole thing of which bounding boxes you want to draw, you do not want to draw, and finally you are left with those bounding boxes you want to draw. So you had the non-max suppression algorithm. So non-max suppression is basically what means is, if you have 2 or 3 boxes or more boxes pointing to the same object, in that case you have to use non-max suppression. So non-max suppression is basically to remove redundant objects, and it does it in a very similar intuitive kind of way. If you think about it, it just calculates IOU, and if those two boxes overlap a lot, that means they both might have actually be pointing to the same class. It is like very intuitive thing, but yeah, you can understand the whole thing. So the whole point about the whole point about this, about fast YOLO is basically, I'm saying about YOLO is basically, see, this is the whole structure. You get 7 cross 7 cross 30. Once you have this, you have the detection procedure. Alright. So this part is basic CNN, and even in this part, only this part is pre-trained. The rest, these 3 layers have to be trained. So each grid gives out you 2 anchor boxes, unlike faster RCNN which gave out 9 anchor boxes. Alright. So you have to decide that, and in the future things, what will happen is, in the YOLO classes this number will increase. For YOLO V1 it was 2 per grid. grid box, all right. And then we calculate all of these values. We calculate these class scores finally by multiplying one, and for each grid you are going to get 2 class scores. So ultimately you are going to have 98 such values. And once you have that, what you will basically do is add a threshold to it and remove those that are not required. Once you have that, the next thing you will be doing is a non-max suppression algorithm. So that is the whole thing basically, and I hope you enjoyed this. And the link to this very interesting presentation will be provided to you. Don't have to worry about that. And yeah, then you can actually go through it and in details understand more about it, but it is pretty intuitive. So that is it. I hope you enjoyed the class and keep learning.